this bit here. Just before the elements started forming from quarks and whatnot to make protons and neutrons and then hydrogen and helium and so on, there must have been something like 1 billion more quarks, 1 part in 1 billion more quarks than antiquarks. If you had, thanks so much, if you had 1 billion antiquarks, you must have had 1,000,000,001 quarks. And then they all annihilated each other except the one that was remaining, and that's the matter we've got. Do you follow me? If they'd been exactly the same number, they'd have all annihilated each other, left us just with radiation and no matter. So no one has a clue why there was just a little tiny bit more of quarks than antiquarks. And yet we needed it to be more or less spot on, otherwise there wouldn't have been a universe like we know it. Incidentally, looking at this same graph again, here's the connection between the Large Hadron Collider and cosmology and whatnot. As you go back nearer and nearer to the beginning, the energies must have been higher and higher, the temperatures must have been higher and higher. And we're getting here to energies that are so high that no one's ever done any experiments yet and no one knows what's going to happen. That's why the Large Hadron Collider has something to do with the Big Bang. We're trying to find out what might have happened at the higher energies and the higher temperatures where no one has any experimental evidence at the moment. Okay? Now, this bit here is a very, very rapid expansion called inflation. It's much more speculative than the rest of what I've been talking about, but it may explain some of these coincidences. Now, the fourth thing I said is this cosmological constant. I perhaps should talk about what the cosmological constant is. When Einstein invented the general theory, he discovered that it predicted that the universe must be either expanding or contracting. He couldn't get it to describe a universe that was stationary and static, which was a problem, because he thought the universe was stationary and static. But he found a clever way of changing the equations. He put in a thing called the cosmological constant, which gave a bit of a push to oppose the pull of gravity. He could balance the equations and make the universe static, so it would neither expand or contract. So he thought that was clever, and he put this number, lambda, into the equations. About 5 years later, they discovered that the universe was expanding, which was a bit sad. And Einstein said, my biggest blunder, if he hadn't put this constant in, he could have predicted the expansion of the universe, instead of which they discovered the expansion of the universe, and everyone dropped the cosmological constant. Well, it doesn't exist anymore. Until they did these experiments with the supernovae, and they discovered, blow me, the universe is accelerating. There is a cosmological constant. There is something which is causing expansion as well as contraction. Now, these numbers I need to try and explain. And again, I should have checked this because it comes out a bit better on the Mac. Sorry about that. When you do particle physics, you can actually predict that a vacuum ought to have energy, the sort of energy which might make the universe expand. There's just a minor problem. And the minor problem is that the number that you get is about that much too big. 1 with 120 zeros. It's the biggest discrepancy anywhere in any physical calculation. When the experts calculate how much the universe ought to be accelerating, they get a number which is 10 to the power 120. 1 with 120 noughts, too big. Okay? Ridiculously too big. I think I may have mentioned that the Higgs field predicts a similar effect, but only 60 zeros, so don't worry about that, because 120 is the one they worry about. Why on earth is it that there is a cosmological constant, but this enormous factor, too small? Imagine calculating it. And how can you get a calculation which gives you 0, 0, 0, 0, 0 for the first 120 places, and then 3 or something? Very remarkable. But it seems as though it's astonishingly small, but just right. Because if the cosmological constant was maybe 10 times bigger than that, it would cause the universe to expand too fast, and you wouldn't get stars and you wouldn't get galaxies. Do you follow me? And if it was the other sign, it would cause contraction and black holes and whatnot. So it really is pretty critical that it's this size. So, I mentioned inflation, and this very rapid expansion, very near the beginning, 10 to the minus 32 seconds, that's a millionth of a millionth of a millionth of a millionth of a millionth, just a second, right at the beginning, this very rapid expansion by a huge factor, millions and millions and millions and millions of times, could explain some of the things that we've observed. It would be caused by a very high vacuum energy. And there are theoretical reasons. People can invent ways which could give rise from particle physics to this very high vacuum, which would cause a very rapid expansion of space. And if it happened, it would naturally explain why the universe has a very flat geometry. It's not a flat universe, but an exact balance. You know, that thing had to be, the Big Bang, if you like, has to be very precisely tuned. This inflation business actually explains it naturally. Anything that's curved gets evened out very rapidly. It explains why the temperature is very uniform. And interestingly, in this tiny, tiny fraction of a second, when it's expanding very rapidly, if there were quantum fluctuations, and you'd expect that, they get expanded to actually form the variations that you see in the cosmic microwave. So it explains that as well. So we're talking about this very rapid expansion right at the beginning. We're talking about the very, very precise balance between matter, or the geometry, if you like. And I showed you that cosmic microwave background with the very small variations. Well, this is a plot of how big the variations are at different scales. These are the very big variations, 90 degrees. These are 2-degree variations. These are half-a-degree variations. These are very small ones. And these are the actual measurements of how big the variations are at different scales from that graph that I showed you. And you can see, here's a calculation of what inflation might predict, and it's pretty good. So, you know, it seems as though quantum fluctuations in those very, very early fraction of a second get expanded out to be the seeds of galaxies and stars and planets. So it naturally explains various things. It naturally explains the flat geometry, gives the right kind of spectrum for the variations, so it doesn't actually say how big they ought to be. On the other hand, it's a very clever idea, but no one has yet come up with a proper theory of it. In other words, you can see how particle physics could give this kind of thing, but nobody's actually found a particle or a field any proper solution that really explains it. And my suspicion is that whatever caused it must have been itself fairly finely tuned to give just the right kind of inflation, if it happened. I emphasize, inflation is more speculative than the other things I've been talking about. So, summary at this stage. Most cosmologists think that there is strong evidence for this standard cosmological model. The lambda, which is the dark energy, cold dark matter. It's called cold dark matter because it's not going to be particles like neutrinos going very, very fast. It's going to be fairly slowly moving particles, so they're called cold. So, standard lambda cold dark matter, and most people believe in this very rapid period of inflation very soon after the Big Bang. Now, there are these remarkable, unexplained coincidences. Part of the model, but we don't know why the numbers come out like they are. At this point, just a few provisional comments about how this relates to biblical belief in Christianity. First of all, what about the idea of a vast and old universe? I mean, does it not make human existence entirely insignificant? We are so small in this incredibly large universe, it's incredibly... How could we possibly matter? Well, actually, I think that these discoveries actually underline and expand biblical ideas. Take this from Psalm 8. The psalmist says, "When I consider the heavens, the work of your fingers, the moon and the stars, which you set in place, what is man that you are mindful of him?" In other words, the psalmist thought, the universe is vast. I'm so small, how can you possibly care for me? And yet you do. And we say, how much more? This is one that really appeals to me from Psalm 147. It says this in the same verse: He heals the brokenhearted and binds up their wounds. He determines the number of the stars and calls them each by name. Isn't that amazing? You know, the psalmist says the same God who is the God of the whole lot is the God who cares for me individually. So I say, we believe in so much more vast a universe than he did. Isn't this even more amazing? Here's another bit. Who has measured the heavens in the hollow of his hand, or with the breadth of his hand marked out the heavens? Who's held the dust of the earth in a basket, or weighed the mountains on a scales and the hills in glass? Who's understood the mind of the Lord, or instructed him as his counsellor? Whom did the Lord consult to enlighten him? Who taught him the right way? Who was it that taught him knowledge, or showed him the path of understanding? Surely the nations are like a drop in a bucket. They are regarded as dust on the scales. He weighs the islands as they were fine dust. To whom then will you compare God? So, in the Bible you already have this sense of a vast universe, a God who is greater than we can ever imagine. Nevertheless, he cares for us. And I just think if you like, it expands our imagination. How about this? This is about Christ. He was with God in the beginning. Through him all things were made. He was chosen before the creation of the world, but revealed in these last times for your sake. And you, in him, we were also chosen. The thought that God's plans for us actually started before the Big Bang, I find pretty mind-boggling. But then the Bible's really mind-boggling anyway. So, to me, it's like, my thought is just how much more, rather than can't be true. Secondly, the idea of a universe in which space, time and matter had a real beginning fits in with the idea of creation. See these graphs here. You may say, what happened before this point, according to where did it come from? Well, the theory says, nowhere. That's the beginning. It's not an empty universe in which matter suddenly exploded. It's not a very long time when things suddenly began. No, that's the beginning of space. That's the beginning of time, as well as the beginning of matter. Before then, there weren't any before then. Do you follow me? Hard to imagine, but that's what the theory says. In other words, that's where time and space and matter all began. I think that's quite consistent with the idea of creation, actually. Hard to understand, but finally, these unexplained coincidences. And I go back to Susskind again. Why is it that the universe has all of the appearances of having been specially designed just so that forms like us can exist? And it seems to me that these unexplained coincidences and fine-tuning are consistent with, first of all, belief in a rational creator, a universe that makes sense, a universe that's worth studying by scientific methods because you can believe that laws are going to exist. But secondly, a rational creator who always intended life. Life is not a coincidence, a just utter accident that we're here. It was always part of God's intention. But someone may say, oh, well, inflation explains away this stuff. Well, I think, inflation, first of all, is quite speculative. It's not nearly so well established as the rest of the stuff. But it seems to me, it may be an example of what I would call a deep natural solution. Do I imagine God just saying, I think I need to put an extra 2 on the end here to make it work properly. Let's just make it bang a bit faster and it'll be possible, but I'm much happier with the idea of saying, we could do it naturally. That would be clever, wouldn't it? Let's make a particle which makes it expand by inflation naturally. Do you follow me? A subtle, clever, deep, natural solution. I'm quite happy with that. And I think Christians should be comfortable about this. Explaining something, in my judgment, is not the same as explaining it away. So, there we are for tonight. The plan is coffee and stuff, and submit questions, and we'll come together as soon as possible for continuing question and answer.